Welcome to the course on error control coding and introduction to linear block codes. So, we will continue our discussions on some simple linear block codes. This time we are going to discuss about Reed-Muller codes. We will talk about their construction, we will give an example, we will prove some properties of Reed-Muller code, and then we will talk about decoding of Reed-Muller code. So, for any integer m and r such that r lies between r is greater than 0 and less than equal to m, there exists a binary rth order Reed-Muller code, which we denote by these parameter r and m. Reed-Muller code has following code properties. So, the length of the code is 2 raised to power m, and this dimension k is given by 1 plus m choose 1 plus m choose 2 up to m choose r, and the minimum distance of the code is given by 2 raised to power m minus r. So, let us take an example. Let us take m to be 4 and r to be 2. So, in this case the length of the code word will be 2 raised to power 4, which is 16, and since the order of this Reed-Muller code is 2, so this k will be 1 plus 4c1 plus 4c2. So, this will be 1 plus 4 plus 4 times 3 by 2. So, this will be equal to 11, 1 plus 4 plus 6. So, k is this thing, and minimum distance is 2 raised to power 4 minus 2, which is 4. Now, how do we construct a Reed-Muller code? So, to do that, let us define. So, we are defining an binary m tuple, let us call it Vi. So, for I going from 1 to m, we define a binary m tuple in this particular fashion. So, there is alternating runs of zeros and ones. So, Vi is run of zeros for 2i minus 1 times, then run of ones for 2i minus 1, like that. So, this Vi consists of 2m minus I plus 1 alternating zeros and ones, and where each of these runs of zeros and ones are for 2i minus 1. So, let us take an example. Let us consider m to be 4, m to be 4. So, then this m tuples are 2 raised to power 4, that is 16. Okay. So, what is V1? Now, V1 should have runs of zeros and ones, where this run is 2i minus 1. So, when I is 1, this is 1. So, that means we should have V1 is 0, because that is a run of 1, then followed by a run of 1 for one time, then followed by 0 one time, then 1 one time. So, like that it will continue for this block of 16. Now, what is V2? For V2, I is 2. So, 2i minus 1 would be in this case 2. So, we should have 2 runs of 0 followed by run of 1, which is repeated twice, run of zeros repeated twice, 1, 0, 1. This you continue up to block size of 16. What about V3? In this case, I is 3. So, what will be 2i minus 1? 2I minus 1 would be 4. So, you have runs of 0 for 4 times, followed by runs of 1 4 times, then again runs of 0 and runs of 1. What about V4? Here I is 4. So, 2I minus 1 will be 8. So, we have runs of zeros for 8 times, followed by runs of 1 8 times. So, that is how we define our this binary m tuple for each of these I going from 1 to m. Next, we define a Boolean product. How do we define a Boolean product? Let us say we have two n tuples x and y. So, I am denoting x by x0, x1, x2, x3, xn minus 1. Similarly, denoting y by y0, y1, y2, yn minus 1. Now, we define these Boolean product as, so this is bitwise AND x0 dot y0, x1 dot y1, x2 dot y2 up to xn minus 1 dot yn minus 1. So, this x0 dot y0 will be 1 only if both x0 and y0 are 1, otherwise it will be 0, and same with others. So, xi dot yi will be 1 only if both of them are 1. So, that is how we are defining this Boolean product operation. So, let us take an example. This is our V1, if you recall, this was our V1 and this is our V2. So, if we define Boolean product between V1 and V2, we write it at V1 dot V2, and V1 dot V2 will be 1 only where V1 and V2 both are 1. So, which is like this location, number 4th bit, this location, then this location, and then this location. So, you can see it's only 1 at this 4th, 8th, 12th and 16th location. All other time is 0. This is 0 for all other time. Okay. So, this is how we define the Boolean product. We also define an all 1 tuple. So, this V naught is basically all ones of length 2 raised to power m. Now, for I1, I2, I3, IL which lies between 1 and m, we can define this product vector Vi1, Vi2, Vi3, VIL, where this is basically Boolean product between these Vi's, and we say this has degree L if there are L Vi's which are participating in this product, and weight of this product is given by 2 raised to power m minus L. So, now that we have defined these tuples Vi's and the Boolean product between them, we are ready to define the generator matrix for Reed Muller code. So, an rth order Reed Muller code which is of length 2 raised to power m can be generated by the set of independent vectors, where these vectors are V0, V1, V2, then Boolean product of second order which is V1, V2, V1, V3, these are all second order product, then we will have third order product, fourth order product depending on what the R is. So, we generate Reed Muller code using these 2m tuples basically of these V0, V1, V2 and their Boolean product. And as you can see that V0 is all one sequence. So, there is one such possible ways we can get this. V1, this MC1 ways of choosing, V1 MC2 ways, of, so V1, V2, V3, Vm, this is basically m choose 1, then Boolean product of degree 2 can be chosen m choose 2 way, and similarly Boolean product up to order r can be chosen m choose r ways. So, that is basically the dimension of the code. Now, if we arrange these vectors V0, V1, V2 and the Boolean product up to order r as rows of a matrix, that will be our generator matrix for Reed-Muller code, and each of these V0, V1 and their Boolean product, they are basically linearly independent. So, we can generate our Reed-Muller code using these V0, Vi and their Boolean product as rows of our generator matrix. So, let us illustrate this with an example. We take a case where m is 4. So, m is 4 meaning our code word length would be 2 raised to power m, which is 16. So, we are dealing with Reed-Muller code of length 16, and let us consider second order Reed-Muller code. So, we will have to now recall what is a degree. If you go back, this product vector is said to have degree L if there are L such Vi's which are participating in this Boolean product. So, we have to write all these as rows of generator matrix up to product of degree r. So, this is your V0 vector, these are all your V1, V2, V3, V4, this is degree 1, and then these are all possible degree 2 Boolean product vectors. Because m is 4, so we will have V1, V2, V3, V4 and r is 2. So, we have to consider all possible Boolean products of degree 2. So, that would be V1, V2, V1, V3, V1, V4, V2, V3, V2, V4, V3, V4, and that is what we have listed here. And of course, you have your all one pattern, and these. So, what you are going to do is you are going to arrange these as rows of your generator matrix. So, this is your 11 cross 16 generator matrix, okay, and we will use this to generate our set of code words. Now, this another alternative construction of Reed-Muller code. So, if you are given Reed-Muller code of length 2 raised to power m minus 1, then you can use two of them to construct a Reed-Muller code of length 2 raised to power m. So, how do you do that? So, this is done in this particular fashion. So, if you have two Reed-Muller code, so one Reed-Muller code of order r and length 2 raised to power m minus 1, and you have another Reed-Muller code of order r minus 1 and length 2m minus 1, then these two can be used to construct a Reed-Muller code of order r and length 2 raised to power m, and in this particular way. So, first, so you can, so if this is, so this is one code of length 2m minus 1 and this another code of length 2m minus 1. This is your code u, which is order r, and this is u plus v, where u is given by this and v is given by this. So, in other words, you can construct Reed-Muller code recursively from smaller order and smaller length code. The same thing I am writing in terms of generator matrix. So, as I said, this is a Reed-Muller code of length 2m minus 1, this is another Reed-Muller code of length 2m minus 1. First is just U, which is this code, Reed-Muller code, order R, length 2 raised to power m minus 1, and the second one is this. So, this is your U, which is this, and the next one, this is your V, which is this. So, I can write down, so in other words, I can construct Reed-Muller code recursively from smaller length Reed-Muller code. This is another way of generating the generator matrix for the Reed-Muller code. So, let us prove some of the properties of Reed-Muller code. The first property that we are going to prove is that minimum distance of Reed-Muller code is 2 raised to power m minus r. We are going to prove this result using mathematical induction. So, how does this work? So, first we assume m to be 1, and let us check whether this minimum distance holds correct for m equal to 1. So, for m equal to 1, let us consider two scenarios, one where r is 0 and in second case r is 1. So, when m is 1, what is the length of the Reed-Muller code? It is 2 raised to power m. So, that length is 2. Okay. And when order is 0, so G will consist of only V0, which is 1 1. So, Reed-Muller code of order 0 and M1 is essentially a length 2 repetition code. And what is the minimum distance of this code? It is 2. So, let us plug that in here and see whether it is correct. M in our case is 1 and R is 0. So, this gives us minimum distance of 2, and that is precisely what we are getting. So, this holds true for m equal to 1 and r equal to 0. Now, let us see if it holds true also for m equal to 1 and r equal to 1. Now, if m equal to 1 and r equal to 1, so then the length of the code word is again 2. So, G will consist of V0 and V1. Okay. And what is my V0 and V1? V1 is 0 1 0 1 and V0 is 1. So, this is length 2. So, what I will get is G is 1 1 and this is 0 1. So, this will be my generator matrix. Now, this will generate these following code words of length 2, and what is the minimum distance between these codes? That is 1. You can say minimum weight code word is, minimum weight of non-zero code word is 1. So, minimum distance in this case is 1. Okay. And let us check. So, in this case m is 1 and r is 1. So, 2 raised to power 1 minus 1, 2 raised to power 0, that is 1, and that is what we are getting. Fine. So, then this is true for m equal to 1. Now, let us assume it is true for any m equal to m, and then we will try to prove that it is also true for m equal to m plus 1. So, let us assume that it is true for up to m and for any order where order can be from 0 to m. Let us assume that this is true. So, minimum distance is given by 2 raised to power m minus r. Now, what we are going to show is that this is also true for m plus 1, and what should be the minimum distance for m plus 1? It should be 2 raised to power m plus 1 minus r. So, that is this. So, next what we are going to show you is that minimum distance of rth order Reed-Muller code, Rm plus 1 Reed-Muller code is basically given by this. Now, to prove this, we are going to make use of this construction of Reed-Muller code, that Reed-Muller code of order R and M can be constructed recursively using this. We are going to make use of this construction to prove our result. So, let us see how we proceed. So, let us consider two code word f dash, which belongs to Reed-Muller code of order R and length 2 raised to power m, and let g dash belongs to Reed-Muller code of order R minus 1 and length 2m. Then we are defining two code words, then a Reed-Muller code of order R and length 2 raised to power m plus 1 is of the form we just said u and u plus 1. So, these code word and C1 and C2, which is of the form f and f plus g, f dash and f dash plus g, they must be code word belonging to this Reed-Muller code, and this follows from our recursive construction of Reed-Muller code, which we just mentioned. So, C1 and C2 must be code words for this Reed-Muller code. Now, let us try to compute the minimum distance between these codes C1 and C2, which are code words Reed-Muller code of order R and length 2 raised to power m plus 1. So, first case that we will consider is when g is same as g dash, and second case that we will consider is when g is not same as g dash. So, when g is same as g dash, what is the minimum distance between C1 and C2? Now, if g and g dash are same, then basically your code C1 is nothing but it is f here of length 2m, and this another code word f of length 2m, and C2 is f dash of length 2m, and then you have f dash of length 2m. So, what is the minimum distance between this code? It is minimum distance between f and f dash plus minimum distance between f and f dash. So, that is what we are writing here. So, if g is equal to g dash, the minimum distance between C1 and C2 is 2 times the minimum distance between f and f dash. And what is the minimum distance between f and f dash? F and f dash belongs to Reed-Muller code of order R and length 2 raised to power m. So, their minimum distance should be 2 raised to power m minus r. So, then from this we get that minimum distance between C1 and C2, which are two code words belonging to Reed-Muller code of order R and length 2 raised to power m plus 1, this should be greater than equal to 2 raised to power m plus 1 minus r. So, for this particular case, we have shown that minimum distance is indeed this. Now, we will also have to show if g is not same as g dash, then also we have to show that minimum distance is at least this. So, next we consider the case when g is not same as g dash. Now, if g is not same as g dash, then weight minimum distance of the code we can say basically number of positions where C1 and C2 are differing. This can be written as weight of f minus f dash plus weight of g minus g dash plus weight of f minus f dash. If we are talking about binary codes, this will be basically plus is also fine, because that is the same thing. So, if you have two code words, let us call it C1, which is f here, and this is f plus g, and then you have C2, which is f dash plus g dash, then the minimum distance between code is f minus weight of f minus f dash and weight of this minus this. So, that is what we are writing here, that minimum distance between C1 and C2 is given by this plus this. Now, we also know that let us say if you have two m tuples, n tuples, then weight of A plus weight of B, where A and B are some n tuples, this is basically weight of A plus weight of B is greater than equal to weight of A plus B, right. Now, if I consider A to be x plus y and B to be y, and let us say x plus y, they are all binary n tuples we are talking about, then A plus B will be x plus y, so that is given by x. So, what we will get is weight of x plus y plus weight of y is greater than equal to weight of x, right. Or we can write weight of x plus y is greater than equal to weight of x minus weight of y. Next, we are going to make use of this result to simplify this expression. This you can consider this is my x and this is my y. So, I can write weight of x plus y to be greater than equal to weight of x minus weight of y. So, when I do that, then distance, minimum distance between C1 and C2 is this term coming here, and what did I do? This was weight of x, this was x, this was y, this I can write as this is greater than equal to weight of x minus weight of y. So, this weight of x is this term minus weight of y, which is this term, fine. So, now this cancels out, what I get is weight of g minus g hat. Now, what is g? G belongs to Reed-Muller code of order r minus 1 and length 2 raised to power m. Then what is the minimum distance of this? So, what is the minimum distance between g and g dash? This should be 2 raised to power m minus r. What is r? The order here is r minus 1. So, this is r minus 1. So, this is 2 raised to power m plus 1 minus r. So, what we have shown is even when g is not same as g hat, our minimum distance is still 2 raised to power m minus r plus 1. So, now we have proved that minimum distance, if minimum distance of rth order Reed-Muller code of length 2 raised to power m plus 1 is basically given by this. So, this will conclude the proof using mathematical induction that the minimum distance of Reed-Muller code is 2 raised to power m minus r. The next result which we are going to show you is that m minus rth order Reed-Muller code is the dual code of rth order Reed-Muller code. So, let us see, this is our original code, then the dual code is given by this. Now, what do we need to show for dual code? If we take a code word from this code and if we take a code word from the dual code, they are orthogonal, right. So, the dot product should be 0. Another point which I should mention here is, let us go back to our construction of Reed-Muller code here. Please note the way these Boolean products are constructed. In fact, we just proved also the minimum distance of the code is even, is 2 raised to power m minus r. So, minimum distance of Reed-Muller code is even. So, Reed-Muller code would not have odd weight code words. So, now we will show if we take a code word from m minus r minus 1 nth order Reed-Muller code, and if we take another code word from rth order Reed-Muller code, then they are orthogonal. That is the first thing we are going to prove. So, let us consider code word A which belongs to m minus r minus 1th order Reed-Muller code, which is of length 2 raised to power m. And let us consider another Reed-Muller code B, which is of order r and length 2 raised to power m. So, A can be viewed as a polynomial of degree m minus r minus 1 or less, and similarly the degree of the polynomial B is less than equal to r. So, if we consider their product, then this will be a polynomial of degree m minus r minus 1 plus r. So, that would be of degree less than equal to m minus 1. So, then this product A and B will belong to a Reed-Muller code of order m minus 1, and this is of length 2 raised to power m. Now, note that Reed-Muller code has only even weight code words. So, when we are considering this dot product A dot B, since Reed-Muller code has only even weight code word, then A dot B would be 0. So, modulo 2 this will be 0. So, in other words, then what we have shown is, if you take a code word A which belongs to m minus r minus 1th order Reed-Muller code, and if you take another code word which belongs to rth order Reed-Muller code, then they are orthogonal to each other. Next, we check the dimension of m minus r minus 1th order Reed-Muller code and rth order Reed-Muller code, and we see that sum of their dimension is 2 raised to power m, which is the length of the code word. So, this does prove then that m minus r minus 1th order Reed-Muller code, let us just write an m here, is dual to rth order Reed-Muller code. Now, let us see that some of the codes that we have studied are actually a special case of Reed-Muller code. So, the first thing which is clear from the construction is that any r minus 1 order Reed-Muller code is a proper subcode of an rth order Reed-Muller code, and thus this is easy to see if you noticed and go back to our code construction. What was our generator matrix? Our generator matrix consists of these tuples V0, V1, V2 up to product of degree r. So, if we are considering 0th order Reed-Muller code, this will only have V0 in the G matrix. If we are considering first order Reed-Muller code, it will have V0 and it will also have V1, V2, V3, Vm. If you are considering second order Reed-Muller code, this will have this and it will have all these second order terms. So, you can see that smaller order Reed-Muller code is already embedded in the larger order Reed-Muller code. So, from the construction you can see that smaller order Reed-Muller code is essentially a proper subcode of a larger order Reed-Muller code. So, this relation holds, and this can be easily seen from the construction of Reed-Muller code. The 0th order Reed-Muller code is a repetition code. This we have shown earlier also. Note that for the 0th order Reed-Muller code, your G matrix will only have this V0, which is all ones, and that is precisely the generator matrix for repetition code. M minus 1th order repetition code, M minus 1th order Reed-Muller code is actually a single parity check code. Again, this is easy to see, we can just use the results that we have proved. we know that M minus R minus 1th order Reed-Muller code is dual to the rth order Reed-Muller code. So, if R is let us say 0, then it is dual to M minus 1th order Reed-Muller code. So, 0th order Reed-Muller code is dual to M minus 1th order Reed-Muller code. And what is the dual of a repetition code? It is a single parity check code. So, M minus 1th order Reed-Muller code is nothing but a single parity check code. Similarly, M minus 2 order Reed-Muller code is our extended Hamming code which we just talked about in the last lecture. So, let us discuss how we can decode Reed-Muller code. So, we will illustrate the decoding of Reed-Muller code through an example, and we are going to use what we call majority logic decoding. So, let us consider the Reed-Muller code with parameter M equal to 4 and R equal to 2. So, in other words, the generator matrix will then consist of V0 all first order VI's and these Boolean product of order 2. We already know how to get this V1, V2, V3, Vm, we just talked about that earlier, and we also know how to compute the Boolean product. So, this is essentially our generator matrix G of a 2-4 Reed-Muller code. Now, the message that we want to encode, let us call it A0, A4, A3. This is how we are denoting the message that we are going to encode, and since the rows of our generator matrix are given by V0, V1, V2, V3, V4 and this. So, our code word would be linear combination of rows of the generator matrix. So, that we are writing denoting by A0 V0 plus A4 V4, A3 V3 and similarly A34 V3 V4, A24 V2 V4. So, this is how this is linear combination of these 11 rows of this generator matrix, that is how we will generate our code words. So, this 16th length code word is basically linear combination of these rows of our generator matrix. Now, we will spend some time looking at the generator matrix and we will use some observations from the generator matrix to decode our code. So, what are these observations? So, first thing we will see if we see the first 4 components of each generator vector and subsequent groups of 3 groups of 4 consecutive components, they are 0 except for vector V1, V2. What do I mean by that? So, let us look at this group of 4. This is group of 4, this is group of 4. So, what I am saying is, if you look at this group of 4 and if you add them up, let us look at this first group of 4. This will be 0, some will be 0, 0, 0, 0, this is 1, this is 0, 0, 0, 0, 0. You take any such 4, this is 0, 0, 0, this one is 0, this one is 0, this is not 0, again this row, this one is 0, 0, 0, 0. So, you take any such groups of 4, this one is 0, 0, 0, 0, 0, this is not 0 and these are all zeros. Similarly, this is not 0, these are all, if you add up these, they are all 0, 1 plus 1, 1 plus 1 plus 1, these are all 0. Same here, 1 plus 1, 0, 1 plus 1, 0. So, if you look at these bits, 4 bits at a time, you will notice except for this one V1, V2, all others are 0. Now, how can we make use of this fact V1, V2. So what we will do is, if we add up those first 4 elements, the contribution from all others will be 0, except because V1, V2 is non-zero. So, we will get contribution from what A12 is. So, in other words, these code word bit then can be written as, so if I am calling this bit at 0th location as 0, bit at first location as B1, second location B2 and B3, then by adding the first 4 bits, I can get information about what A12 was, and this can continue for next set of bits as well. So this is, let us say, B0, B1, B2, B3, this is B4, B5, B6, B7, this is B8, B9, B10, B11, this is B12, B13, B14, B15. So, if I add this B0, B1, B2, B3 or B4, B5, B6, B7, B8, B9, B10, B11 or B12, B13, B14, B15, what I am getting is contributions from all other rows are nullified, only I will see the contribution effect of this V1, V2, and the bit A12 can then be found by adding these 4 columns together. So, I can get information about A12 by looking at these first 4 columns or first 4 bits of this code word. Similarly, the next 4 bits of the code word, if I add them up, I can get another independent information about A12, and same thing I can get from the next set of 4 coded bits. So, what you can see is I am getting 4 independent views about what A12 is. Now, the decoder can take a majority logic decode. If there is no error, of course, all of them will tell me about that A12 is the same bit, whether it is 0 or 1, but if there is a single error, what you will notice is, in some of the bits, let us say there is an error in some bit location B1, then A12 here would be different from what A12 I am getting from other 3 equations, and then I will use majority logic decoding. What is majority logic decoding? So, I will take the majority decision. If 3 of them are saying A12 is 0, then I will go for 0, otherwise I will go for 1. Okay. So, this is how I can decode bit A12. So, and this will be repeated for decoding other bits as well. So, let us say my received bit is R0, R1, R2, R15 corresponding to the transmitted bit B0, B1, B2, B15. Then I can decode A12. How? I will just add these first 4 bits, then I add the next 4 bits, next 4 bits, next 4 bits. So, I am getting 4 independent views about what A12 is, and then I will take a majority decision. Majority of them are saying 0, I will go for 0, otherwise I will go for 1. Now, the same thing, exactly same way I can decode other bits. So, let us look at A23. So, if we look at A23, let us look at this row, maybe I will use a different pen. Let us look at this row, this row, this row and this row. So, if I add bits in this row, this will be 0, this will give me 0, this will give me a 1, this will give me 0, this will give me 0, this will give me 0. So, you can see all rows will give me 0 except this particular row, and same thing I can repeat for, if I look at second row, fourth row, sixth row and eighth row, I will get the same information. So, if I look at, now let us say I look at this row. If I look at this row, this row, this row and this row. So, this will give me 0, this will give me 0, this will give me 0. Now, here this is a 1, this is a 0, this is a 0 and this is 0. So, this will give me 1 and all other rows will give me 0. So, if I add up these bits, 4 bits at a time, in similar fashion I can get independent information about A23. So, again the point to be noted here is, what you need to do is you look at this and find out basically like combinations of these received bits, which will give information about one particular transmitted bit and not others. And once you do that, you can similarly do for other bits. I have just listed here. You can verify yourself that if you add these bit location, you will get independent information about A14, similarly for A24 and A34. Now, once you have decoded A12, A23 or once you have decoded all of these, again remember the way we are decoding is, so we are getting 4 independent views about the same bit, majority of them are saying it is 0, we go for that, or else if majority of them are saying they are 1, we will go for that. So, once we have decoded these sequences, let us just subtract the contribution of these bits from the received signal. So, the new received sequence which we are calling R1 is the actual received sequence minus the contribution from these Boolean product terms subtracted. Now, once we do this, then what we are left with is essentially we are left with this. So, we are now left with decoding A0, A4, A3, A2 and A1. So, first we try to decode the rth order terms, then we try to decode r minus 1th order term, and finally, so here we first decoded the terms related to the second order. Now, we will try to decode these terms which are related to the first order, and we will again follow the same procedure. What we are going to do is, we are again going to look at this G matrix and we are going to look at the bit. So, we are now looking at, because the contribution of these have been removed, so we are now looking at this G matrix. We are only looking at this, assuming we have correctly decoded A12, A13, A14, contribution of these have been removed. So, only we think we are left is this. Now, if you notice, if you add up 2 rows like this, consider these 2 rows. So, what you would notice, for all other except V1, we will get 0. So, in other words, I can get 8 independent views about what A1 by just looking at these 2 columns of this matrix. So, I am getting 8 independent equations for A1, and again I will go for majority logic decoding. So, whatever majority of them are saying, I will decide in favor of that, and the same procedure can be repeated to find out what A2, A3, A4 are. Again, this is just a typo, this should be A2 here, and similarly this is A3 here. And this is A4 here. Okay. Now, this is exactly same procedure I followed for A1, we are using for A2, A3, A4, A4, and then we are getting independent equations, 8 independent equations, and we take majority decision in decoding these. Now, once we have decoded A1, A2, A3, A4, we will then remove the contribution of this from the receive sequence. So, our receive sequence R1, we remove this. So, what we are now left is the term containing V0. So, we are only left with A0. So, now we have 16 opinion about A0, and again we take a majority decision, and that is how we decide in favor of A0. So, this in a nutshell how we are decoding a read Muller code. So, first we try to decode the rth order terms, then r minus 1 and like that, and the key is look at the generator matrix, and from there try to find out combinations of bits which will give independent opinion about a particular transmitted bit. So, with this I will conclude this discussion on read Muller code. Thank you.